In the next 5 modules, I'm going to go over some specific pitfalls of p-values. I'll start with something called statistical significance versus clinical significance. Many people don't realize, but it turns out you can get highly statistically significant results, that is very, very, very small p-values, even if you have really tiny trivial effect sizes. Remember, the p-value depends on effect size, variability, and sample size, all 3 of those things. So it turns out that the sample size, if it's big enough, can completely drive your p-values. It turns out if you have a huge, huge sample size, you are able to measure things so precisely that you can detect the tiniest little difference between groups. Those differences are real, but they're just so small that they're clinically meaningless. They're not useful. This is the idea of statistical versus clinical significance. You can't just look at statistical significance. You also have to consider how big is the effect. Is it big enough to be clinically meaningful? This whole concept is best illustrated with an example. Let's return to the example that I started to talk about in the teaser for this week. This was a study that appeared in the Journal of the American Medical Association in 2010. It's a prospective cohort study of 34,000 women, so notice it's a very big sample size. The researchers followed the women for about 13 years to track their weight changes over time. This is a longitudinal study. They wanted to know about the weight changes over time. The researchers divided the women up into 3 exercise groups: a high exercise group, a medium exercise group, and a low exercise group. The high exercise group exercised about 60 minutes or more per day of moderate intensity exercise. It turns out that the high exercise group gained significantly less weight over time than the other 2 groups, both the medium and the low exercise groups, and the p-values were highly statistically significant. This study received a wide amount of attention in the media. The headlines were things like, "To stay trim, women need an hour of exercise daily." "New exercise goal, 60 minutes a day." I asked you in the teaser to think about how big do you think the effect was? Again, highly statistically significant, but notice I haven't told you yet how big the effect was. How much less weight do you think that the high exercise group gained compared with the low exercise group over 3 years? And the reason it's over 3 years is that the researchers in this study measured the women every 3 years, so they calculated the effect size in 3-year intervals. So I asked you to make a guess about the size of the effect. So think about your guess now. The answer, the size of the effect, might surprise you. I'm going to show you the table that gives the results of this study. There's a lot going on in this table, so let's just zoom in on this table. This is the table right from the study. I'm zooming in on the thing I want to talk about, the overall results. The researchers here did an excellent job in their statistical analysis. They did a really elegant statistical model. Remember, the women were measured over time, and the researchers measured them every 3 years. So they measured their physical activity levels every 3 years. They also measured their weight change every 3 years. And the beautiful thing about this statistical analysis that the authors did is that they allowed the women to change groups over time. So they incorporated the fact that a woman might have started as in the high exercise group, but later went down to the low exercise group and then might have gone back to the high exercise group. All of that is captured in their statistical model. So it's a wonderful, elegant, repeated measures regression model. They also did a great job of presenting their results in a way that's very easy to understand. So it's a rather complicated model, but they've presented the results rather nicely. So let's just go over the results that are available to us in this table. Because everything is done in 3-year intervals, the effect sizes are the weight changes in a 3-year interval. So what are we looking at in this table? The reference group, first of all, is the high exercise group. That's why we have a 0 here. That's the reference group. So everything is compared to the reference group. What you're seeing in the table here, here's the high exercise group. Here's the medium exercise group, and here's the low exercise group. And what you're seeing in this table is this value and this value. These are the mean, the average difference in weight gain between the low group and the reference group, or between the median group and the reference group. And this is in kilograms. In other words, and this is in a 3-year period, over a 3-year period, the difference in the weight gain between the high group and the low group was 0.15 kilograms on average. The difference between the high group and the medium group on average was 0.12 kilograms. Now, if you're like me, I don't really think in kilograms, so let's translate that into pounds. What was the effect size here? Those who exercised the least in the low group gained 0.15 kilograms, or 1/3 of a pound more than those who exercised the most over a period of 3 years. In other words, that's 1/10 of a pound more per year. 1/10 of a pound, which is a very, very tiny amount. This was a 13-year study, so we could even try to say, well, maybe that's just too short of a time. What if we project this over like a long time? How much weight can you save yourself by exercising an hour a day over 13 years? Well, if we extrapolate that about 0.3 pounds, about 1/3 of a pound every 3 years, that's over 13 years, you could save yourself about a pound of weight gain over 3 years. Certainly, that's not going to solve the obesity crisis if you can prevent 1 pound of weight gain only. So this is a classic example of a statistically significant effect. Notice the p-value here, very highly significant. A statistically significant effect that is not clinically significant. This is a real effect, so the high exercise group really did gain less weight over time, but the amount of weight that they saved themselves was so small. It's clearly not where we're going to want to put our money in terms of solving the obesity crisis. That's a very small payoff for exercising an hour a day. Now, I'm all for exercise. I'm a runner. I totally support exercise, and it's great for many things in your health. But this study is showing that that its effect on weight gain over time is really, really small, at least for women. So what's going on here? It really surprises people when they see, well, the p-value is so significant, but the effect size is so small. How can that be? Well, remember the sample size in this study. This study looked at 34,000 women. Not only that, but it measured each woman multiple times, so the number of observations incorporated in the model is over 100,000. That sample size is so huge that there is such great precision here that the researchers are able to detect even the tiniest differences between the groups. These are real differences. They're just so small. Again, it's not where we want to put our money in terms of solving the obesity crisis. It's always helpful to pay attention then, not just to the p-values, but to the effect sizes and the 95% confidence interval. The point estimate here was 0.33 pounds. I'm going to do everything in pounds because I think in pounds rather than kilograms. It's 0.33 pounds over 3 years. That's how much weight you could save yourself by exercising an hour a day versus none. The 95% confidence interval for that estimate ranged from 0.09 to 0.44 pounds. That means that the effect could plausibly be as large as a 0.44 pound reduction in weight gain over 3 years. If there's anything in the confidence interval that's big enough for us to care about, that's clinically meaningful, then we might say that that's, a large enough effect. But if there's nothing in the confidence interval that's big enough for us to care about, if the highest that it's plausibly could be is only 0.44 pounds, then clearly this is not a clinically meaningful difference. The upper bound of that confidence interval is not big enough for us to, again, want to put our money on exercise as the measure of weight gain prevention. And one of the reasons I absolutely love this study is because it has a wonderful picture. And I mentioned at the beginning of this course the importance of drawing pictures. And this study happened to have as one of its figures a beautiful graphic that kind of tells the whole story. This is one of the cases where the fancy statistical model led people astray, whereas the graphic nailed it. So what are we looking at in this graphic? Again, this study was all about weight gain over time, longitudinal changes in weight. You're looking at this graphic at the 3 exercise groups. So the low exercise group is the top line, the medium exercise group is the middle line, the high exercise group is the bottom line. Notice that at baseline, there was huge differences between the 3 groups. So cross-sectionally at baseline, the high exercise group by far is much lighter than the other 2 groups. That tells you that cross-sectionally, there is a relationship between exercise and weight. But remember, with cross-sectional studies, we don't know the direction of cause and effect. Perhaps people who are lighter find it easier to exercise, or other factors going on here. What this study was all about was measuring the trajectory over time. What happened in terms of over time? Notice that the over time trajectories, if you look at these lines, well, they're almost beautifully, perfectly parallel. So what does that tell you? That tells you that the pattern of weight gain, the weight gain trajectories over time, are almost identical between the 3 groups. Now, you might look at this figure and wonder, well, how could the authors have missed that? Well, they didn't miss it, okay? They looked at their picture, they interpreted the picture correctly. So let me show you their interpretation. They write clearly in their article, Figure 2 shows the trajectory of weight gain over time by baseline physical activity levels. When classified by the single measure of physical activity, all three groups showed similar weight gain patterns over time. So they completely recognized what this graphic showed them. What their argument is they're saying, oh, if you just classify people according to their baseline exercise status, then the weight gain is identical. But remember, their fancy statistical model did something wonderful. It allowed women to switch groups. So some women who started as high exercise group in the high exercise group could switch to the low, could switch to the medium. Their model incorporated that. So what they inferred was they said, oh, well, these lines are clearly parallel. But it was impossible on the graphic to show the switching of women between groups. But our fancy statistical model captured that. Oh, and we got that significant result on our fancy statistical model. So it must be that the reason this graphic doesn't capture that is because it doesn't in any way show how women are switching around groups. My argument would be that actually the graphic nailed it, and the fancy statistical model actually nailed it too, but you have to pay attention to the effect size and not the p-values. So I don't really think that this graphic, the reason that those lines look parallel, has anything to do with the fact that women are not allowed to switch groups in this graphic. And you can kind of show that. I think it just has to do with that the effect size is so small that you can't see a difference in the slopes visibly. And the way to show that is actually just to look at the first 3 years of the study. So the way the model is set up is that your exercise level in one 3-year interval, at the beginning of one 3-year interval, is supposed to predict your weight change over the next 3 years. Well, look at the first 3 years of this study. Their model says that the baseline physical activity should predict the weight gain in the first 3 years of the study. Now look at those 3 lines. Those look about as parallel to me as 3 lines can be. Why is that? Well, remember, the effect size is so small here, a 0.15 kilogram or 0.12 kilogram difference in the slopes over 3 years. It's so tiny that it's not visibly perceptible. So again, looking at the picture and trusting the picture more than the fancy statistical model can really serve you well. Let me just go through a little bit of how this can happen. Again, it really surprises people that statistical significance isn't directly telling you about effect size. People think, oh, it's highly statistically significant, it must be a big effect. But remember, that's not the case because there are 3 things that affect the p-value and statistical significance. There's effect size, but there's also sample size and variability. And roughly, statistical significance, how small your p-value is, how statistically significant you are, is proportional to effect size, and sample size end up in the numerator. Remember, because if you think about the way we calculated p-values, effect size is in the numerator, standard error is in the denominator. But what's standard error? It's roughly equal to variability divided by sample size. So actually, since sample size is in the denominator of standard error, that ends up in the numerator. Statistical significance is proportional to the effect size and to the sample size. So a really big effect size can drive statistical significance, but a really, really tiny effect size, as long as that effect size is not 0, any small number can be compensated for by a huge sample size. So if your effect size is 0.00001, whatever, I don't know what the units are there, but your sample size is, 1 million, it might be that comes out to be statistically significant. It's completely driven by the sample size. Huge sample sizes will detect tiny effect sizes. And I like to illustrate this by using the correlation coefficient. We talked about the correlation coefficient last week. That's a number that ranges between -1 and +1. -1 is perfect inverse correlation. +1 is perfect positive correlation. 0 means absolutely no correlation. It turns out that whether or not the correlation coefficient comes out to be statistically significant, we're just going to be statistically significant here at p is less than 0.05, whether it achieves that p is less than 0.05 depends on only 2 things. The size of the correlation itself. Remember, this is a unitless quantity, so it doesn't matter what we're measuring. The correlation coefficient is always the same because it's unitless. Depends on the size of the correlation itself and the sample size of the study. That's it. There's a little approximation that I've used here. You can show that roughly, for most cases, the correlation coefficient has to be, in order to be statistically significant at the 0.05 level, it's directly related to 2 divided by the square root of n. And we can put this in a chart and illustrate this. So if you have a sample size of 10, Any correlation coefficients that are below 0.63 will not come out to be statistically significant. Any correlations that are above 0.63 will be statistically significant. For any study, again, because we're talking about a unitless quantity here. That's a pretty moderate to large size correlation. If you have a sample size of 100, though, any correlation above 0.20 is going to be statistically significant. If you have a sample size of 1,000, a correlation above 0.06, which is a really small correlation, will come out statistically significant. If you have a sample size of 100,000, any correlation that is bigger than 0.006 will be statistically significant. That is a tiny, tiny correlation. Remember, 0 means no correlation. We're essentially at 0, but it's just enough away from 0. And if the sample size is big enough, you can show that that's a real correlation, but it's so small as to be meaningless. With a million, a sample size of 1 million, a correlation of 0.002, is statistically significant. So we can show that there is something there that's different than 0, but it's just because we've measured things so precisely that you can see a difference between 0 and 0.002, but 0.002 is still essentially no real correlation. It's so small. Another headline just to illustrate these. These are really fun, I think. Here was a great headline. Drinkers may exercise more than teetotalers. This was great because it's implying that it's a cross-sectional study, so they weren't exactly implying that if you drank more, you would exercise more, but they were suggesting maybe that drinking more would help you exercise. Of course, cross-sectional, so we don't know the cause and effect direction. There may be confounders, but it's a cute headline. Drinkers may exercise more than teetotalers. The survey showed that as your activity levels rise, you tend to drink more, the increase in alcohol use. Let's read a little bit into the article. Here's something to toast. Drinkers are often exercisers. They briefly describe the methods. In reaching their conclusions, the researchers examined data from a large survey study. It's a yearly study of about 230,000 Americans. So notice, huge sample size here. So again, I'm going to ask you, what do you think the effect size was here? Well, we read a little bit further in the article. At least this article actually gave the effect size. Some articles don't. Here was the effect size for women. If you drank versus if you were a teetotaler, women who drank exercised on average 7 minutes more per week than teetotalers. In other words, again, it's a statistically significant difference between drinkers and non-drinkers, but is 7 minutes of exercise a week really going to make a difference? One of my students said, well, that must be the, them getting up from the couch to go to the beer to get the fridge. That's the extra 7 minutes of walking that they got per week. So you can see funny things happen if you only pay attention to the significance level. You have to think about whether the effect size is big enough to matter. So my take-home points here, p-values, remember, what were they designed for? They were really designed to help us distinguish between real effects and random fluctuation. And this was an important distinction when you're talking about sort of moderate size samples. Sometimes we're not sure if something is chance or if it's real, and p-values can help us distinguish those. But if the sample size is humongous, in fact, random fluctuation is no longer an issue. If the sample size is humongous, we're not really worried about things happening just as a fluke. We're able to nail down very precisely the effects. So it turns out that in really, really large sample size, p-values are essentially irrelevant, and I would just ignore them. And we're talking about sample sizes in the tens or hundreds of thousands, which are not uncommon these days. Now, the exception to that is, think about the vaccine, the HIV vaccine study we talked about last week. That had a sample size of 16,000. But this idea of huge sample size doesn't actually apply to that study, because what's important in terms of the sample size when you have a binary outcome is how many people actually had the event. Remember that only 125 people came down with an HIV infection. So the fact that the background sample size was 16,000 is not really relevant here. The p-value was useful in that case because we only had 125 events, and that's the sample size that's relevant, is that when you have rare outcomes is actually how many people had the outcome. But if you're talking about sample sizes of tens or hundreds of thousands in terms of the events or in terms of just the total sample size, when you don't have a binary outcome and you have a continuous outcome like weight gain or how much exercise you do per week, essentially you should ignore p-values. All the p-values are going to come out statistically significant, but they're meaningless because the effect sizes could be really, really small. So pay attention, in particular when you have large sample sizes, but always, even for any study, pay attention to the effect size and the confidence interval. And what you're really looking for is if the confidence interval doesn't contain any effect sizes that are big enough to care about, essentially this is a clinically insignificant result. If it's statistically significant but clinically insignificant, it's not something that we're going to, again, want to change policy on. We're not going to want to put our money on something that's clinically insignificant, that doesn't really change things in a meaningful way.